to my talk, Cooperative Context Switching in the Cloud, or How to Build a Multi-Tenant Microservice. So what's the point of this? We want to show you how possible it is to sort of migrate from an on-prem library to a multi-tenant API in a microservice. We're going to talk about multi-tenancy in a concurrent world, and also using a coroutine library, in this case, Greenlets, for performance. We're going to use these three libraries, gevent, workzug, and ZeroMQ today. We won't cover async IO or any of the new Python 3.5 async keywords or any callback-style asynchronous programming models. And really just consider this discussion a starting point for many other people who are facing this sort of similar situation where you have an on-prem library, an on-prem application that you then need to sort of cloud enable. So who am I? Navin Kumar, as was introduced. I've been working full-time with Python since 2013. My company is Inside Engines. We started in 2015, and our goal has been to make machine data accessible using natural language. So to get started, I'll just give you a little brief primer on our technology. So we're a natural language product. So what we do is we start out with a natural language query. That query is then parsed by our proprietary parser into an intermediate language. That intermediate language is then fed into a compiler, and that compiler outputs a query, a database query in this case, to sort of access data. And so you can think of these two combined together as our natural language engine. For the parser, you need sort of a domain dictionary, some lexicon, basically. And also, we also incorporated a spacey model and spelling correction models, so we can do dependency parsing and part-of-speech tagging as well. And so all these together form the model that we'll talk about the rest of this talk. Also, for natural language, you need a context. You need a customer context. So that improves our ability to parse queries and make the most optimal database queries. So again, we need models for understanding queries. We need a domain dictionary. In this case, we focused on cybersecurity and IT. And sort of this customer context, the information about our customer environment. Since we're in cybersecurity and IT, we need computer host names, user information, basically login accounts. We also enable our customers to customize the dictionary so they can point their own terminology to specific custom things in our environment. We also collect data quality information so that we can generate the best possible queries for their platform. So to start off with, we were an on-prem application. You'd install our software as an add-on into a data platform. In our case, it was the Splunk platform. And we embedded our natural language in this add-on, essentially. And essentially, this was, the customer would actually download this add-on themselves and install it into their own site, basically. And there's a lot of limitations behind this. The installation process for this add-on was very complicated. We had to package this add-on to sort of obfuscate our proprietary technology. And so this was very difficult. Many of our customers had specific change windows, so that essentially meant that it had to be after hours and once maybe every month in some cases. So just we couldn't update them quickly enough. We also couldn't push any updates automatically. So it was really difficult to add new capabilities and fix bugs that would show up in the product. And also add synonymous language. So sometimes to handle a specific use case, there'd be multiple ways to ask that question. And this is important for natural language systems. If you've used Google Assistant, Siri, or Amazon Alexa, you notice that they're constantly being updated and new functionalities being added all the time. So our solution is, just like those products, we had to move to the cloud. So going from our on-premise application, we then turned our application into an API client, and we took our natural language engine and put it behind a REST API. So to start off with, we could do a naive version of this. Remember, our natural language engine is an on-prem library, so we can just use it like a library. So we moved this thing behind a REST API, and then for each request, we'd load the customer data and then create a new instance of the natural language engine to serve each requesting user, and so on and so on. So to start off with, I'm going to show you this sort of naive implementation. But first, I'll just show you briefly. Here's some code. And you can see here, this is sort of my version of our natural language engine. You can see here there's a context variable, attribute that's being set here. And then we're accessing a function on that context attribute called getValue. And in I'm using Flask here for implementing the API. We create a new version of that context, and we create a new version of that engine, essentially for each and every request. And we're waiting. So this is really, really slow. And there's a reason why this is slow. So every time we have to basically build a new version of our natural language engine, we have to train a model, or load a pre-trained model essentially into memory. In this case, I kind of cheated here and I added a sleep. But this actually corresponds to how much time it took for our natural language engine to preload its model. So obviously, this is untenable. I mean, you can't have, the startup cost of building a new version of this object is just not something that is suitable for a production environment. You can't have each customer waiting 5 seconds or 10 seconds or however much time it takes to load this model into memory. So one thing we have to ask is, what if we could share that natural language engine? What if we can take that startup cost and make it happen only once, and also happen before any customer actually queries the natural language engine? We also want more flexibility. We want to deploy more than one version for testing. We want to support new domains beyond IT and cybersecurity, where the lexicon information there could be conflicting or whatever. So different customers, we want to give them different versions of the product. So this kind of informs our architecture choice of microservices. So instead of your monolithic REST web application, you then take your natural language engine and model and move them each to their own microservice. So you front this thing with a REST API, and using some RPC transport layer, you actually feed different microservices in this environment. So in this case, we're feeding the first version of our model in this version, and then the second version of our model in another version. We can just use a test group for this, or we can even have other microservices that are behind this API. So again, why? It's componentized. We can replace and add microservice components over time. We can have multiple versions, multiple architectures even running simultaneously. And we can scale each of these things separately. And also, for our natural language engine, we can support this custom behavior. So, for example, our natural language engine can preload its model into memory behind this microservice. Now, how do we make this multi-tenant? We only want to keep a handful of these engines in memory. In this case, one. In some cases, you may want more than one. A couple of considerations. Your code has to be suitable for a concurrent environment. That's number one. This is the concurrent world. You got multiple requests coming in. Your code's got to be reentrant. And we also require specific information about each customer. So we have to be able to load that information on demand still. This enhances our ability to answer questions with higher precision, and we'll call this a request context in the world of a multi-tenant application. So how do we maintain your concurrency and throughput and still service each customer optimally? So the first case, the first try at this is using worker threads in a pool, right? Many modern client-server applications have used a form of thread pool. For example, the HTTPD, Apache, actually one of the most basic configurations of Apache is just a thread pool of several workers. Threads, many of you probably know this about threads. Each one has their own stack, their own registers, own context, basically. And really, they're optimized to provide parallelism on multi-core platforms. And they're available in almost any modern programming language. So, we can make our NL engine thread safe, but how do we handle this request context that I just described? So this kind of borrows a concept that's been around for a while called thread local storage. Essentially, this is static or global memory that's local to a thread. You can think of this as a global variable, but the value is unique for each thread that's actually being used. In Python, the class for storing these thread-specific values is called threading.local. So here's a brief example of that. You can see here, I'm creating my sort of threading.local object. And there's 3 threads involved here, the main thread and the 2 threads that I'm forking here. In this case, we're sort of printing around this sort of assignment here. So when there's no value that's assigned to this, you'll see no value. And then after it's been assigned, obviously, you'll see the value. And so the output of this, just for clarity, this is not exactly the output of this. It's kind of like this. Because of threads, this 1 could be here and the 0 could be here. But you can see here that for each thread, that unique value is there, right? So when we fork the first sort of thread from the main thread, there's no value in that threading.local, and then we set 1, and there's this new value. So all these values are isolated from the other threads. We also needed a transport layer for RPC, so we used ZeroMQ. It's abbreviated ZeroMQ. You may have seen it. It's abbreviated as the number ZeroMQ or ZeroMQ. It's written in C++. It's got bindings in almost all major languages. And it really allows you to easily build concurrent network-based applications. There are also some useful integrations, and I'd like you guys to hold this thought. We'll show off some of these later on. We use it, again, in our production implementation. So now, going back to sort of our natural language engine briefly, we turned our context here into an abstract base class. And then what we do here is we actually sort of check, we do a bit of a type check here just to make sure that it's like an appropriate thing. And we've renamed our old sort of context class to simple context here, just so that we can use this thing in its original form. You can see here, using ZeroMQ, we've actually turned our sort of API into something that actually just talks to our microservice. It's listening on localhost 5559, and it's using a ZeroMQ socket. This is sort of how this library works. It's sort of like sockets on steroids. And going back to sort of our microservice, you can see here our microservice essentially now implements a threading local subclass that actually implements that sort of context interface that we defined before. So we actually registered as a virtual subclass here. And using sort of ZeroMQ, we fire off some worker routines, and they will initialize this context with our customer ID. We also have this sort of reset functionality here, which we'll talk about in a bit, because this does have an effect on how this works. But essentially, this thing will then load the original sort of simple context and then proxy values into that context based on the customer ID passed in. So, and using ZeroMQ, you can actually use threads pretty easily, and there's some complicated socket work here that I won't get into, but essentially with this sort of multi-part socketing, you can actually then fire off requests to each of your individual worker threads. So you can see here, it's much faster. I can even change sort of the identifier, and you'll actually see a different host name that's being used here. I'll increase the size. And over here, you can see another one. And so this is the same query, but it's actually being fed for it's being used for 3 different customer IDs. So you can see the multi-tenancy at work. So there's an issue here. We're using threads, but there's some issues with Python threads. Many of you have probably seen this if you've ever looked at Python source code or seen a bunch of think piece articles on it, but this is the global interpreter lock. And essentially this means that all C code running inside the Python interpreter must hold this lock while executing Python. So this loosely translates to one thread runs Python while n others sleep or await I/O. This means that a single Python process can't really take advantage of multiple cores. And there's been several takes on this. Bug reports, people have tried to remove, every single attempt to remove this lock has basically resulted in a big argument and basically a bunch of people saying yeah, we can't really remove this because performance in single-threaded applications just gets so much worse, and it's just not worth the gains for multi-threaded. So more on threads. Threads also, we mentioned they have their own machine registers, kernel stack, environment block, all this stuff. This is really unnecessary overhead in a lot of cases. And in a lot of cases, it's just using extra memory. We really don't need this memory for our application. Also, as I showed off before, going back here, we actually had to create this ugly reset method here because to reuse this threading.local and reuse this thread, essentially, we have to reset attributes on the object because they're still unique to the thread, and we don't need those attributes. For the next request, they just have to be memory. They have to service the next request appropriately. So some background on cooperative multitasking. The term coroutine was actually first coined in 1958 by Melvin Conway. He wrote this in a paper basically a publication for ACM magazine called Design of a Separable Transition Diagram Compiler. And this was the multitasking of early operating systems. So early operating systems, you would have processes that would just voluntarily cede control. So they would actually run for a certain period of time, and when they were done, they would say, I'm done, signal the operating system, and then the next one would take over. This was the case for pre-OS 10 Mac OS and 16-bit Windows. Now, this has sort of been changed. Now we're kind of in a preemptive world. Even in the world of Python, which still is, while single-threaded, still has a concept of preemption. In Python 3, it's about 15 milliseconds. There's a 15 millisecond timeout for each thread before it gets preempted. Or in Python 2, it's about 2,000 bytecode instructions. But essentially, it sort of turns Python into sort of a time slicing environment. And also, there's still I/O waiting. And I/O waiting is essentially a cooperative behavior that exists in almost any environment at this point. So whenever you're waiting on I/O, you're still kind of you're basically saying, I don't need to run, and you're telling the OS, I'm waiting for I/O, tell me when it's ready, let something else run. And usually, in these cooperative systems, a process will just call the yield or a sleep method and cede control, or they'll just wait in an event loop, and they'll just basically wait for I/O to sort of signal them to be alive again. So in Python, there's a modern equivalent. It's coroutines, right? And sort of the most basic example in Python is this sort of concept of the generator, right? In this generator, you have this sort of asynchronous world by which you're getting items from some database and you paginate through your database. And then for each item, you're actually then yielding control. You're saying, I don't need control. And then you're sending it back up to this loop thing. So yeah, so this is it's just like any other cooperative environment where you're just telling another function that you're ready to go. And so you've probably seen this in your most database code where you're just paging through a bunch of objects. So we actually chose a library called gevent. It's actually inspired by Eventlet, which is another coroutine library. It was built on libev. It's now based on libuv if you get the latest version of it. It uses the greenlet library. You can think of greenlets as micro-threads. It preserves this event loop cooperative behavior. So essentially, we're getting rid of context switching and replacing that just purely with waiting for I/O. Again, leaving this thread context, time slicing preemption that we had before. It actually uses a similar API to threading. So it's very actually easy to adopt. So go migrate from threading code to gevent code. And because it's event-based, particularly when it comes to sockets, it's highly performative for network applications. It's well maintained. The documentation's at this URL. So here's the most basic gevent socket example. So gevent implements their own implementation of a socket. And you can see here, this is just doing a DNS lookup in a loop. And you're spawning that just like you'd spawn a thread. And then you're waiting for all those things to complete before you then output the IPs. And then gevent can also do things like monkey patch. So you can monkey patch the socket library and then use something like URLub2, which is in the standard library. And this will allow you to use gevent behavior for things that use sockets in the standard library. And the only caveat here is that your code has to be entirely gevent compatible in order to use this. Now, we're actually missing a specific API. This threading.local class does not exist in gevent. So enter WorkZug. This is a library for actually developing HTTP, WSGI applications in Python. Here's the URL. It forms the base of the popular web framework Flask. So we just showed you a Flask application in our example here. And so same thing, it actually forms the base behind that. And developers of this language actually saw the limitations of thread local storage, especially with greenlets. And they realized that we need to create our own local that is sort of more compatible with request contexts in the gevent world. So here's the basic example. You'll notice that just like your sort of threading.local, you can bind an attribute, and then any subsequent access to that attribute in the same context is actually, will resolve. Now, in this case, these things are a little bit more limited than threading.local. You have to manage them just with the managing object. There is a way to sort of get around this management. In general, you should manage them, but there's a function called release local where you can kind of use it like a threading.local. So show you sort of the final implementation of this. So my API actually implementation hasn't changed at all. But behind it, in my ZeroMQ microservice, I created a new subclass called context local. And this subclass is the WorkZug local object. And in the reset method that I had before added, I changed it to just release local. And you'll notice here, ZeroMQ provides a really useful sort of version that is actually Greenlit compatible, called ZeroMQ Green. And it essentially implements most of the same API that the original ZeroMQ like main socket threading library uses. And so you just kind of call all the same functions, but instead of using ZeroMQ just by itself, use ZeroMQ.green. There is a slight caveat to this. ZeroMQ.proxy does not work with ZeroMQ Green. That's a known bug. And so we can actually, so I have this already running here, and it's sort of the same behavior as before. So, putting this together, we got our API. It uses an RPC to talk to our natural language engine inside of a microservice. That microservice then fires up about 5 or so greenlets here. Could be any number depending on how many you think you can, how much throughput you think you can get. And then a customer request comes in using REST. Then we'll then update the greenlet with that context. And then subsequent requests get served by other greenlets as well. So, in the future, we greatly simplified the interactions of threading.local, workzug.local. We use that release local, function to kind of shortcut us. But there's going to be further complications. You'll have to sort of manage these things, and sort of your application will sort of determine what you have to do. We didn't discuss database access today. Database access and library implementation can create a lot of complication that is kind of a little bit beyond the scope of this. Notably, we've run into this, the psychopg2 module. It allows customizing the wait callback to add greenlet support, but the psychopg2 code is not green thread safe. So it's not quite reentrant in the green thread world. So, there's several frameworks that have built-in sort of gevent support. We showed off ZeroMQ.green. The Flask library has gevent support built in because it's built off of WorkZug, again, built into that. Some application server, the UWSGI server in particular, actually supports automatically doing that monkey patch call that we actually showed off in the early example. And if you even use something as new as the gRPC framework, it actually has experimental green gevent support. And some of these frameworks, like Flask, even have their own set of context locals. Flask has something called Flask globals. It's usually accessible using the G attribute of the Flask module. And it's accessed just like a global variable, but it's the global variable that you can use to sort of store information. The request object in Flask is also a global variable, so it's also available for that purpose. But you may have some issues sort of modifying that variable versus the Flask globals variable. So again, depends on your app. Be aware of the documentation. And other coroutine frameworks is Eventlet that I mentioned earlier. It predates gevent, but uses a lot of the same principles, just uses a very different API. It's not quite a Python threading kind of API. It's a bit of a different API. And it kind of has, some people are less comfortable sort of adopting it versus gevent. There's the Tornado library, which provides callback style async. Python 3 actually has async IO now, and async await was added in Python 3.5. And as of right now, I would say if you're using Python 3.7 and you're in your application, I would highly recommend using async IO now, because now you get context variables in Python 3.7 that are very useful. And so you can get all this functionality in the standard library if you're using Python 3.7. So I would update this and highly recommend using this if you're using Python 3.7. You can still use gevent in Python 3 if you want to, if you're also more comfortable with that API, which is more thread-like. That's also up to you. But again, your mileage will vary. I would highly recommend using 3.7 for performance reasons. And that's it.
Have 5 minutes, so if someone has a question, please raise your hand and I will reach out to you. Is any question? No, I guess. So that's all. Thank you very much, and have a round of applause for Navin.